Hi everyone. I hope all of you are doing great today. Um, Welcome to our first session, and today we are going to look at a very core concept, which is called system design. System design is very interesting because it helps us to not only understand the engineering aspect of the kind of projects that already exist, but also it gets to give us a perspective on how we can be able to properly engineer our own product solutions. So, system design covers quite a number of things, from the architectural aspect of products or systems to the flows, components, scalability, and also be able to understand some of the real world patterns. That basically means from an overview of the already existing system solutions, we'll be able to learn from there. So, right now, most of us really understand that there's quite a number of projects out there, from YouTube to WhatsApp. We have Instagram, we have Telegram. There's quite a variety of software projects out there, and what's so interesting about them is the number of you know um, of users in those solutions, or rather in those products. For example, if you talk about YouTube is used globally, and right now, the number of users at YouTube is over 5 billion, which is crazy. You can look at other platforms like Instagram, like Facebook, like WhatsApp. You might be interested to also understand, the data aspect around them. So these are just some of the key perspectives that we are going to learn today from what we call system design. So I want us to look at the complete engineering guide here, and this is very comprehensive. It contains what we call engineering guide to system design, and it covers the architecture, flows, components, scalability, and also the real world patterns. So let's look at the table of contents here. So first of all, we're going to look at the overview bit. Then we're going to understand what is system design. Then we look at core objectives, types of system design, flowchart symbols and meanings, system flow fundamentals, high level architecture, low level design, data flow. So data flow is where I was trying to picture out how the users in those platforms get to key in their data and how it's actually moving from one end to another. So we look at this, but from an MVP level, based on the case studies that we will be looking at. Also, there's what we call authentication flow. Then we have scalability design, database design, caching strategy, load balancing, microservices architecture, error handling, security architecture, performance optimization, deployment architecture, monitoring and logging. Then we have what we call system design interview checklist. So this is also very important, especially for people looking to secure jobs in various tech companies to build systems. It will help you to understand some of the questions that you're required to answer as you go through that process. Then we have overview perspective here. So you realize that system design defines how software systems are: one, structured; two, scaled; three, secured and maintained. So system design defines how software systems are structured, scaled, secured, and maintained. So it answers quite a number of questions. One is how components interact. Remember, components are more features. So how these features do interact is very important. How data flows from the input to the last bit, the output, and then how failures are handled. For example, if there's a downtime, how is it handled? Those kinds of questions are very important. And then how systems scale. For example, if you have an MVP and you've realized that the number of users actually scaled to or has increased maybe from 1,000 to maybe 100,000, how do you get to sustain that system in a way that it's feasible, right? That is why system scaling is very important. And then how performance is maintained also is very, very important. So system design is not coding, for those who are actually interested to know. This is not about coding. It is about engineering decision making. It's all about you trying to sit down and trying to ask yourself very critical questions and trying to engineer that. So that is why we call it system design. You have to really sit down and think through it. For example, before you get to build a house, you have to design it, right? And that is where architectural design comes in. You need to really, really sit down, understand the plans, the sitting room, the layout of the bedroom, the backyard, you know, and all other things. So that is the work of architectures. Their work is to sit down and design the actual layout in a very perfect way. So system design is not coding; it is actually engineering decision making. And as you continue, you realize that you'll be building a lot of knowledge in design to a point where it will be very easy for you to be able to not just understand various types or rather various levels of design, but also you'll be able to be very detailed in how you're able to capture the features, the components, and making sure that they are all in the right spaces or other places. So I know most of you are very surprised up to this juncture. You're trying to imagine an app like WhatsApp. Why do we need to get to the system engineering aspect? Remember, um, all the softwares that you see out here, they're engineered. It's just like how you can engineer or rather design a car and get it out there on the road. Same case with a house or any other engineering product that you can see or rather identify around you. Softwares operate the same way. So system design is a very key thing because without designing the actual software, it's very hard for you to even get to the coding bit. Coding is basically just you sitting down to build. Nothing crazy about it. It's just you using the actual programming languages, tools. They could be open source tools. You sit down and now build the software. But the design aspect is where the work lies. And you remember, anytime anyone is trying to come up with a new idea, for example, if we talk about the already existing software solutions out here, most of them are actually solving a key problem in the community or rather in the society. And as they're doing that, you realize that how they get to do it is very, very different, or rather, very, very. So, up to this juncture, we are still trying to make sure that you can be able to understand what system design is, and also ensuring that the engineering aspect is very clear. Because remember, before you get to build anything, you have to sit down and design it. So, let's get to understand what system design actually is, right? So, system design is the process of one, defining system components. That is one very important thing, actually. System design is a process of one, defining system components, which means you have to understand what are these core components that are required for me to be able to come up with a very unique system. And then two, designing interactions. So these interactions comes from other built from the components, right? So you have to understand your core components, and then now you have to understand how the interactions look like. So if it's about features, you have to understand the functionalities of all these features and how they interact together. So if we're talking about maybe a software like WhatsApp or Instagram, we're going to see how the core components are interacting together. How without them, it's very hard for us to be able to properly come up with a more structured ecosystem. And then choosing technologies. When it comes to technologies, this basically means the kind of programming languages that you're going to use, the kind of tools you're going to use, are they open source tools? You really have to be clear about the technologies you're going to use. And then planning scalability. Planning scalability. At this juncture, we're trying to understand how can you effectively come up with mitigations on how you can be able to scale your product. For example, if you have a software that houses around 1,000 people, or rather has 1,000 users at this juncture, now your main question will be, how can I be able to increase that number to 100,000, for example? And how can I be able to scale my product to ensure that it can be able to sustain 100,000 users? So scalability is very, very important. And when you're building, or rather when you're designing any system, you need to ensure that you think through that clearly. And it's very critical because sometimes things might get out of hand and you find it very hard to be able to understand, or rather come up with a very structured way of going about it. And then we have what you call handling failures. Handling failures. How do you get to handle failures, right? Just in case there's a breakdown. How do you get to handle that? Very, very important. So system design exists at two levels. One, we have what we call the high level design, that is HLD. And the purpose of high level design is to come up with a more structured architecture and components. So this is very, very important, especially when you really have a clear layout of the kind of product you want to build. You need to come up with a high level architecture and ensuring that all the key components are structured well to ensure that there's some interaction around them. And then there's what we call low level design. So we have the high level design, then we have the low level design. So for the low level design, here we're looking at things to do with classes, APIs, logic. And you realize most of the MVPs that we get to create, MVPs basically means minimum viable products. Most of the MVPs that we get to create, they have classes, APIs, logic, but then at a low level design. But now when we have to elevate to a high level design architecture, now we have to uh, picture out how all these key uh, things are going to operate, from the APIs, the logic around the operations, right? The classes, and that system architecture really has to come out strongly. So that is in regards to high level and low level design. So the purposes are basically clear like that. And then we have what we call core objectives. We have what we call core objectives. So when it comes to the core objectives, these objectives are very distinct, and definitely they have different kind of descriptions. For example, when we talk about scalability, we're talking about how can we be able to handle increasing load in a software, or rather in a product. And that's what I was trying to talk about when it comes to users. For example, if we're looking at a product that already has maybe 100,000 users, and after some time, the numbers increase to maybe a million users, how can you be able to handle that load? Very, very important. So that element of scalability is very, very key. Then we have what we call reliability. Reliability. So this one means operate without failure. So anytime there's some issues with your software, and rather maybe downtimes, for example, how can you ensure that even if the downtimes down or the software will still operate without a lot of pressure? That aspect of reliability is what we're trying to picture out here, and it's very, very important. So operate without failure, reliability, that's very key. Then we have what we call availability. So in availability, this one means we're trying to minimize downtime, right? Very, very important. And then we have what we call maintainability. How easy is it to update our software? Then we have performance. In performance, we're looking at the fast response, right? Response. Then you have security. So for security, we're looking at data protection, very, very important. Then we have cost efficiency. And under cost efficiency, we're trying to see what is the minimal amount of resources required to build the software, or rather, what is the minimal resource usage. For example, if your software has been consuming, let's say, around $10,000 every month, right? How can we come up with measures of ensuring that we can be able to cut the cost down to maybe $1,000 a month. So that is also very, very important. And at the same time, even with the cost cut down, it still gets to achieve its purpose without any issue. So that is a very important area to look at. So these are some of the core objectives that system design really, really helps us um, to look at. And you realize now it's not all about just building a software. There are some key things to really, really appreciate, especially the design aspect as we continue. So every engineer building any software out there who is doing so well, you need to appreciate them because all the software that you're seeing out here, they have some high level engineering that is very, very critical. So now we have what we call types of system design. I think we've been able to have an overview of these two, where we have the high level design and the low level design. I would like to talk about the high level design part, that is the HLD. So, high level design aspect talks about the architecture, the services, data flow, the technology stack. When I talk about architecture, I think up to this juncture we already have an understanding of what the architecture actually entails. Architecture basically means how can you ensure that the key components are interacting together perfectly well, and at the same time, the services that are actually being offered there are cool. So that is very important. The architecture, services, data flow, technology stack. So an example could be client to an API gateway, then an API gateway to services, then services to database, right? Client to API gateway to services, then services to database. So we will try to understand how this architecture actually looks like. Remember, um, we expect that the client, in one or another, is inputting some data, and this data has to be passed through the API gateway. Then this API gateway has to prompt out some services, and these services have to be, prompted from the database and then reversed back to the client. That is how the architectural aspect looks like. So this is just a simple example of a high-level design architecture. Then we have what we call a low-level design architecture, and this one defines one, classes, two, APIs, three, data models, four, algorithms, and five, error handling. So low level design is also very, very important because it helps you to not only understand classes, APIs, data models, algorithms, error handling, it helps you to understand how they connect together too. Very, very important. And this one, you realize that they tend to operate in any application, be it an MVP or even a high level software product that you're trying to build. That is in regards to the high level and low level design. I would like to look at the I would like us to look at the flowchart symbols so that we can also be able to understand how can we be able to create our own flow, or rather data flow, to guide other people on how they can be able to understand it, right? So we have symbols, we have names, we have meanings. Anytime you see an oval basically is a symbol that means terminator. So meaning the start or the end most of the time. So when you're coming up with the data flow, the oval is where you start from, and you can also end with the oval down there. So just try to picture out a data flow from scratch, right? Then we have a rectangle. So rectangle basically signifies the process, right? So it means action, right? Very, very important. Then we have diamond. So diamond, it signifies decision, decision. So it could be a yes or a no, a yes or a no. Then we have parallelogram. Parallelogram basically signifies input or output, input or output. So this basically means data input or data output. Then we have an arrow. So an arrow basically signifies the flow line, and it shows direction. Very, very important. And then we have a circle. We have a circle. So circle basically is a connector, and it's more of a flow link. It's more of a flow link. So that is why it's very important for us to note that any design, or rather any building, right, that already exists out here, from the house to the cars to the any engineering product that exists around us had to be designed first. Anything that exists around us had to be designed first from the core engineering aspects, and that is very very important for us to note. So, Faith and Kevin, that is one thing that we are really heavy on today. And um, some of the things that you'll be able to notice that when you personally have to come up with your own flowchart diagram, you need to ensure that the kinds of symbols that you're working with are clear and they symbolize the most important thing in your design. So, for example, here, when you talk about an oval, so an oval basically means terminator, or the start, or end. Then rectangle means process or action. Diamond means decision, where it could be a yes or a no. Parallelogram means input or output, or rather data input or output. Then arrow means flow line or direction. So arrow basically just shows the direction of something from one end to another. Then we have circle. So circle basically is a connector. It's more of a flow link. Then we have cylinder. Cylinder basically is a database. It showcases databases. So all these symbols, they have their names and their meanings, and they all symbolize something, and that is why it's very important for us to understand what do they symbolize and why do we need to have them. So hexagon, it's all about preparation or initialization, right? That is all about it. Then trapezoid is a symbol for manual input or human input. Then cloud is more of an external system or a third party service. So these are some of the symbols that you'll be meeting more often. And they're very important for you to be able to note, because even as we continue, you'll be required to start designing your own projects, or rather your own softwares. And these are the kinds of symbols that you need to get used to, because of the meaning that they all symbolize and how you're supposed to go about them. So that's why it's very, very important for us. Um, Unless there's a question there. So there's also what we call the basic system flow. And this is a very basic one because it helps you to understand something from a very basic level, or rather from a very basic flow. One is start. So here we have start. So start basically means user gets to input their data of something, right? So start, then user input. So whatever the user is going to input here will lead to something else. So this basic system flow helps you to understand that um, every approach that you take leads to something else. So this is why when you talk about every cause has an effect. This is why it really lingers clearly, because um, anytime you see a user input, it means that there's something that this user actually did, right? Then there's the validation bit, where now the user input yes, then there's the validation, then there's the business logic, then there's the database, and then now there's the output. So it's a very basic system flow that helps you to understand how data is flowing from the start to the output down here, right? So there's the user input, there's the validation, there's the business logic, there's the database, and then there's the output. Thereafter, we have what we call high-level system architecture, right? And here we're looking at the user. So the user gets to interact with the front end. So the front end here basically could be web or mobile, right? And then after that, we have what we call the API gateway. Very, very important. So at the API gateway, this is now where it gets to connect with the backend services, and then the backend services get to connect with the database. One thing about this system architecture is that it's also well, we can call it high level architecture, but when you try to understand it from a very open mind, you realize that for any user, you need to first of all interact with the front end. The front end could be It basically for a website or a mobile application, right? It's just what you can be able to see in front of you. That's the front end. And then now you get to access the API gateway through the front end, and then you query whatever it is that you need, right? Which means that the API gateway will help you to connect with the backend services, and then the backend services will connect with the database, and then back to the user. So that is how the architecture operates. And you definitely need to understand that everything that's going on here is very uh, intentional, or rather very detailed in terms of the kind of effect that is required. Then we have what we call low-level design structure. Low-level design structure. So here we're looking at controller, service layer, business logic, repository layer, and then the database. So what goes on here? We're talking about a low-level design structure, and this one can operate from a very basic level, right? That's why we have a controller, service layer, business logic, repository layer, and then databases. But then you can see there are no arrows, right? So it just gives you an overview of how the low-level structure might actually look like, but then it's not that serious. That's why it's very low level. But some of the things that are very, very important are here. Controller, you as the person trying to control the product or rather the software, and then you want to query maybe a specific service, and this service has to be queried in a business logic, right? So business logic could be what do you want to make a payment? Do you want to maybe receive payment? Do you want to maybe prompt something? So it has to now respond through the repository layer, which definitely has to connect to the database, but it's very low level. Even how it's been explained, you can see it's very low level in terms of even the explanation. But it's clear. It's very clear for anyone who doesn't even want to get things crazy. This is it. Then we have what we call the data flow design. So under the data flow design, this is also a very interesting area. Remember, um, up to this juncture, we already have a very clear perspective on system architecture. And now we're looking at data flow design. So data flow design, here we have client request. We have a client request. So this client is trying to make a request through the API gateway. Is trying to make a request through the API gateway. And then the API gateway has to, go through the authentication bit. This authentication bit will go through the business logic, and then the database, then the response formatter, and then the client. Very interesting, because this one helps you to understand how the flow actually goes from the client request to the API gateway, the authentication, then we have the business logic, then database there, then response formatter, and then client. Very important. So that data flow design is very, very interesting because it helps you to really capture things from a very clear perspective, right? And as you can see, now this one helps you to even understand things from a more clearer perspective. We expect that the client is operating from the front end, and the front end basically is what they are able to see. That is what we call the front end. And once the client has been able to query in their data, or rather the information, it will be checked through the API gateway here. And then from the API gateway, we have what we call the authentication. So the authentication is what prompts the business logic to now go through the database, and then the database goes to the response formatter, and then now back to the client. So the data flow basically goes like this, and this is what I was trying to explain earlier on when talking about the system architecture and how it operates. Right? So that's about the data flow design, and it's a very important area to look at. And then we have what we call the authentication flow. The authentication flow. When we talk about authentication, we're talking about how do you get to maybe sign up, log in, and things to do with that. So here we have the user who gets to log in through a form. Very important. And then here from the login form, there's the authentication server. So the authentication server helps you to authenticate who this user actually is, right? Thereafter, there's what we call validate credentials. So validate credential part here will help us to confirm if this actual user is authentic. Very important. And how does that happen? There's what we call generation of JWT tokens. This is what helps us to come up with a much more authentic um, credential of who this user is. And then there's a return token, which is now delivered to the protected routes, right? So it helps us to now access these protected routes. One thing about authentication flow is that it's a very important area to look at, especially when designing your systems. Because remember, there are some key areas that most of you won't be able to access. When you talk about the admin section and the maybe the client section, and also maybe the vendor section. This is majorly for maybe BNPL. It could be a buy now pay later system, which has almost four operations. So remember, there's the client section, there's the admin section, there's the merchant section. All of them have a different authentication aspect. So this flow really is important because it helps you to understand how the design aspect looks like from the user login form, authentication server, validation of credentials, generation of the JWT tokens, then the return token bit, and then now accessing the protected routes. So let's look at some of these key components. Under the key component sections, we have what we call JWT, then we have refresh tokens, and then we have session expiry, and then we have role-based access. And most of these key components, they have different perspectives, right? Because all of them have doing different functions. Like the JWT operate differently. The refresh tokens, they operate also differently. The session expiry do operate differently. And then there's the role-based access, very, very important. So these key components are very, very important. Then we have what we call scalability design. So here we are looking at the horizontal scaling and the vertical scaling. So we need to understand, first of all, what is the horizontal scaling. So here, we're basically trying to add more servers, right? And adding more servers requires what we call a load balancer. Very, very important. So in horizontal scaling, we have to add more service, and this requires a load balancer. So we need to understand how can we be able to balance our load in as much as we'll be adding more service. And that is why scalability design is very important. Remember earlier on when I shared about the numbers, increasing in a specific software. For example, scaling from 1,000 users to 10,000 users, from 10,000 users to 100,000 users, from 100,000 users to now maybe a million users. That height of scalability design really is important. So how you get to add more service on that layer is very key. And this requires what we call a load balancer. And that's what we are actually really talking about here. Then we have what we call vertical scaling. So in vertical scaling, here you're trying to increase the server capacity. So here you realize that there will be some limitation to scalability because you're trying to increase the server capacity. You're not trying to increase more service. And up to this juncture, you might be interested to know which is the best scaling method, right? I'm not so sure if you've asked yourself that question. Do you think um, which is the best scaling method? Why do you prefer vertical scaling to horizontal scaling? Thank you for sharing with us about vertical scaling being the most effective. We would like to know here your, comment. I mean, your perspective on it. Why do you feel it's the best? Because it has unlimited scalability. You've said horizontal.
Yes.
Okay. Um, because it has unlimited scalability. Good. Someone else? Someone else was
One
also.
that has, excuse me,
Yes, yes.
the one that has vertical scaling is, the one that has limited scalability is vertical scaling, and he's saying horizontal scaling.
Okay. Okay. Um, let's hear from the other people remaining. Someone else? Someone else? So let's try again. Faith. Just a minute. My mom is giving me a call. Let me answer this call. Is that okay? I was talking about data flow design, and so far we've been able to look at what we call client request, API gateway, authentication, business logic, database, response formatter, and then also we have client. Then we have what we call authentication flow. So this is a very interesting area to look at because first and foremost, you're able to look at the user, then the login form, and then the login form gets to take you through the authentication server. Then the authentication server gets to take you through the validation of credentials, then how you can be able to generate your JWT tokens, how you can be able to return your tokens, how you can be able to access protected routes. Very, very important. And some of these key components, we have the JWT, we have the refresh tokens, we have the session expiry, and also we have the role-based access. Very important. There's also something very critical that we really need to talk about, and that is scalability design. So I think we've already talked about this. I don't know why I went back. We've looked at all this from horizontal scaling, vertical scaling, load balancer flow. Good, good, good. So when it comes to load balancer flow, I think we were at a vertical scaling. So let's look at the load balancer flow. Um, when it comes to the load balancer flow, we have the user requests. Faith, are you here?
Yes, I'm here.
Oh, sorry. I think my volume was a little bit low. Willis, are you here? And the others, are we here? All of us. So there's what you call the load balancer flow, and when you talk about load balancer flow, we're looking at what we call user requests, and then also we're looking at load balancer. So in load balancer, we have what we call server one, server two, and server three. So let's look at database design. Under database design, we have what we call types, which is SQL, NoSQL, cache, object storage, and then we have use case. So under use case, we have structured data, large scale applications, fast access, and also we have media. Very important to note. Then we do have what we call database scaling. So how do you get to scale your database? One, we have read scaling, where you get to read replicas. And then we have write scaling, where you look at things to do with shading, right? Or rather shading. But shading is the key thing here. And then we have caching strategies. Caching strategies. So when it comes to caching strategies, we're looking at user, cache, then database. You as the user, you get to cache, and then you get to do that from the database. So which are the types of tools to actually consider when looking at this? One of them we have Redis, and then we have meme cached. We have Redis, then we have meme cached. So what are some of the benefits? One, faster response. Two, reduced database load. Very, very important. And then now we have the microservices architecture. So under the microservices architecture, we have the API gateway where we're looking at the auth, then orders, then payments. So this API gateway helps you to access the orders and the payments. So Microservice architectures are very, very critical when it comes to how you're operating your solution, your software, your system, sorry. And they have various kinds of benefits and challenges. First of all, I would like us to look at some of the benefits of microservices architecture. One is independent scaling, two, fault isolation, three, faster deployments, right? We're talking about independent scaling, fault, or rather fault isolation, faster deployments. So some of the challenges here, one is network latency. Two is data consistency. Three is monitoring complexity. Very, very important. And we have what we call error handling flow. Error handling flow. So under error handling flow, we're talking about request, then process, then from process we get an error, or rather an error message, which is a yes, for example, which takes you to a log error, and then it asks you to return the safe message. So how you get to handle your errors is very important, because trying to understand you as a client, rather you as the user, there's a request you have to key in, and it has to be processed. As it's being processed, it will be able to indicate that there's some errors popping up, and then there's some log errors somewhere there that really have to be considered, and then now there's the return safe message. So error handling flow is very, very important. And then we have security architecture. So under security architecture, we have layer, and then we have purpose. For layer, we have the first one is HTTPS. The purpose of it is to secure transport. That is the function of the HTTPS. I'm talking about security architecture. I know this is a very interesting area to look at. Most of us really don't, try to put this into consideration. We have HTTPS, which helps you to secure transport. Then we have auth, which helps you to, focus on identity. Identity means, are you trying to authenticate the payment section, the gateway, depending with how you have structured your system. And then we have authorization, where we're looking at permissions. Then encryption, where we're looking at data safety. And then we have rate limiting, where we're looking at prevent abuse. And then we have logging, where we're looking at auditing. So these layers and these purpose, they all align together. And as you can see, they're very critical on how you get to operate. And then we have what we call performance optimization. Performance optimization. So up to this juncture, we expect that, where we already have our system, and now we are trying to optimize it. We are trying to optimize its performance. So how do we get to do that? One is through caching. Two is through indexing. Three is through async processing. Four is through CDN. And lastly, it's through load balancing. So that's how you get to do performance optimization, which is also very, very important. And then now we have deployment flow. When it comes to deployment flow, you need to understand the process from scratch. You as a developer, you need to understand, how do I get to go about my deployment flow? First of all, you need to access the Git repository, and then you have to do a CI/CD pipeline, then testing, then production. Basically, that's the flow. That's how the deployment flow actually looks like. And then we have what we call monitoring and logging. Monitoring and logging. There's some tools to use when you want to monitor and log through your product, or your software. One is Prometheus, two is Grafana, three is the ELK stack, four is Sentry. And the metrics here are: one, we have latency; two, we have error rate; three, we have throughput; and lastly, we have uptime. So this monitoring and logging are key things to also look at, because they help you to understand how you can, the kinds of tools to use, how you can, the kinds of metrics to also check, and ensure that you can be able to monitor and access your software in a more perfect way. There's some of the checklists that I would like us to also note, and actually, this is because we are almost coming to an end of this session here. There's some of the interview checklists to look at, and most of them are very important, especially in system design. I know with time you'll be able to learn about them. One is requirement clarified, requirements clarified. Two is architecture defined. Three is scalability addressed, very important. Then four is bottlenecks identified. Then five is trade-offs explained. Then we have diagrams drawn and failure handling explained. So these system design interview checklists are very important, and on your free time, you can try to understand them. From the requirements clarified, architecture defined, scalability addressed, bottlenecks identified, trade-offs explained, diagrams drawn, failure handling explained. You can name them. And then we have what we call core design principles. Core design principles, one of them we have simplicity first. Two, we have design for failure. Three, we have scale horizontally. Four, we have measure everything. Five, we have optimize later. Six, we have document always. So these are some of the core design principles to also look at, right? From the first bit to the last bit. Simplicity first, design for failure, scale horizontally, measure everything, optimize later, document always. So that is the last bit when it comes to this, because it helps you to understand the real world engineering thinking from this design approach that we have already looked at. And also, it helps you to understand how interview grade system design approach looks like. And again, it helps you to understand the production ready architectural logic, because up to this juncture, as you can see, we've been able to look at quite a number of things here. And this table of contents is very, very detailed in how everything works, from the overview, the system design, the core objectives, the types of system design, flowchart symbols and meanings, system flow fundamentals, the high level architecture, the low level design, the data level, the data flow design, the authentication flow. You can name them. I can still have some time here. There's something very interesting that I wanted us to look at, and I wanted us to look at our sub case study. Before we get there, I would like to get a few questions. There's something very interesting about system design, and most of us have been using WhatsApp for a very long time. Even right now, you guys are using WhatsApp, right? There's something about WhatsApp that I want us to learn today. I want us to learn the WhatsApp system design aspect. So here we have what we call mermaid diagrams, and these mermaid diagrams are a little bit unique